Hello friends, myself Nalinikanta Jana, Senior Lecturer in Physics, Bharuneswar Mahavidyalaya, Utkal University. Today's topic is forced oscillation, which is in our Core 2 Physics Unit 2. In our previous class, we have already discussed about simple harmonic motion and damped vibrations. In case of damped vibrations, we have discussed what are the resistive forces acting on a body executing in SHM. And in that case, we have discussed that one resistive force which is due to the oscillation of the body and is due to the restoring force acting on the body, and that force is directly proportional to the negative of the displacement, that is F proportional to minus y implies F is equal to minus Sy, where S is the constant of proportionality and is known as the stiffness. Okay? This is one resistive force which acts on a body in damped vibration. Another resistive force is also there which varies directly with the velocity of the body, that means F proportional to minus dy by dt, where dy by dt represents the time derivative of displacement, which is nothing but your velocity, and the negative sign indicates that the force is opposing in nature. Now, if we equalize this, then we can write F is equal to minus R dy by dt. Now, we got two forces which act on a body vibrating in SHM, and these two forces are opposing in nature, and that is why the equation of motion for the damped oscillation can be expressed as m d square y by dt square minus r dy by dt minus sy is equal to 0. This is the differential equation of damped vibrations. But what are forced oscillations? Forced oscillations, as the name signifies, we should guess that there must be an external force acting on the vibrating body executing SHM. Then what type of force is this? If literally we will express the forced oscillations, then it will be like forced oscillations are the phenomena of setting a body into undamped oscillations in a resistive medium by applying a strong periodic force whose natural frequency is different from the natural frequency of the oscillating body. Once again I am repeating, what are forced oscillations? Forced oscillations are the phenomena of setting a body into oscillations like undamped oscillations in a resistive medium, that means there are resistive forces present under the action of a strong periodic force. As the force is periodic, hence it has a time period, also it has a frequency whose frequency is different from the natural frequency of the vibrating body. Now, a damped oscillation can become undamped only when a strong periodic force acts on it. As we know, the equation of motion for damped oscillations is like this, then this 0 signifies that there is no applied force, and hence this motion, this equation represents damped oscillations. But today's aim is to make a damped oscillation undamped, and this can be done with the help of a strong periodic force applied on the executing body. So, if a strong periodic force is necessary, then let us consider the force to be in the form like this: F is equal to F0 e to the power I pt, where F0 is equal to maximum value of force applied and P is the angular frequency of applied force. Now, if this periodic force is applied on a damped oscillation, then the motion becomes undamped, and hence this equation can be modified into the new form as m d square y by dt square minus r dy by dt minus sy is equal to f0 e to the power I pt. Now, let us compare this equation with this one. This equation represents the differential equation for damped oscillation, and this equation represents the differential equation for undamped oscillation, and this is known as your forced oscillation because this term represents the applied force. Okay? Now, we have to find out the solution of this forced oscillation. The solution of a forced oscillation will be expressed in terms of y. Let us choose the solution in the form of y is equal to a e to the power I pt. Let us choose the solution as y is equal to a e to the power I pt, where a is equal to amplitude of oscillation. Now, our aim is to solve this equation to get y. Then what we have to do? We have already chose y is equal to a e to the power I pt, but in this equation there are the terms involving the first order and second order derivatives of y. So, let us first take the derivatives of y with respect to t. Now, dy by dt will be equal to how much? D by dt of a e to the power I pt, which is equal to a e to the power I pt into ip, which is equal to ip into y, because a e to the power I pt is y, implies dy by dt is equal to ip into y, implies y will be how much? 1 by ip into dy by dt. Let this is equation. So, this is 1, 2, 3. Now, again differentiating this equation with respect to t, we can write d square y by dt square will be how much? D by dt of dy by dt, which is equal to d by dt of I P into A e to the power I P T, which is equal to I P into I P into A e to the power I P T, which is equal to I square, which is equal to I P into dy by dt, implies as d square y by dt square is equal to I P dy by dt. This is equation 4. Now, putting the values of y dy by dt and d square y by dt square in this equation, we can write m d square by dt square, whose value is I P into dy by dt, minus r into dy by dt, here dy by dt is I P into, once again, m d square y by dt square, whose value is I P dy by dt, minus r dy by dt, minus s into y, whose value is 1 by I P dy by dt, which is equal to f0 e to the power I P T. Now, dy by dt remains at all the terms, hence it can be taken as common, and taking common dy by dt, we can write this equation as dy by dt taken common, then it is I MP minus R minus S by IP, which is equal to f0 e to the power I pt, and here I can be expressed as I plus, so it will be I MP minus R plus I S by P is equal to f0 e to the power I pt. Let this equation is 5. Now, let us substitute. Let S is equal to 1 by C. Let S is equal to 1 by C. So, equation 5 becomes as d by dt dy by dt of I MP minus R plus I by Cp is equal to f0 e to the power I pt. Here we can write, okay, in the beginning what we have written here, this is the damped case and we have applied this force, and these two forces are existing in a damped oscillation. So, this equation can be written as all these forces will be equalized to this, and differentiating these values and putting in this equation, we get m I p dy by dt plus r dy by dt plus s 1 by I p dy by dt will be equal to f0 e to the power ipt, which implies this plus minus, because I is taken offside, so it will be minus I s by p and is equal to this much. Let s is equal to 1 by c. So, putting these values we can write this plus minus is equal to this much. Again dy by dt r plus I taking common, it will be written as mp minus 1 by pc, which is equal to f0 e to the power I pt. Let this is one equation 6, this one is 7, and now this one is 8. Let r plus I mp minus 1 by pc is equal to zm. Let this is equation 9, where Zm is equal to the mechanical impedance Now, putting the value of Zm from equation 9 in our equation 8, we can write dy by dt into Zm is equal to f0 e to the power I pt, which implies dy by dt is equal to f0 by Zm into e to the power I pt. This is equation 10. Just see, what is our aim? Our aim is to derive the forced oscillation equation and its a solution. And already we have seen that the equation for forced oscillation is m d square I by dt square plus r dy by dt plus s y is equal to f0 e to the power I pt. And to get the solution, we have to find out the value of y, for which we have chose the solution of this differential equation for forced oscillation as y is equal to y0 e to the power I pt. And taking its first derivative dy by dt, we have got y as 1 by ip dy by dt. Then taking further derivative, we got d square y by dt square. Now, putting the values of y, dy by dt and d square y by dt in our differential equation for forced oscillations, we will get this much. And we have taken this bracketed term as Zm, where Zm is the mechanical impedance. So, this equation reduces to this much. Now, our aim is to find out Zm, and if Zm is further solved, then we can solve dy by dt, from which we can get y by integrating it. To solve Zm, let us substitute. Let us substitute r is equal to r cos phi and mp minus 1 by pc is equal to r sin phi. Now, from this, by dividing equation 12 by equation 11, we can write r sin phi by r cos phi is equal to mp minus 1 by pc divided by r, which implies r gets cancelled, sin phi by cos phi is equal to tan phi is equal to mp minus 1 by pc divided by r. Equation 13. Further, squaring both these equations and adding, we get r square cos square phi plus r square sin square phi is equal to small r square plus whole square of mp minus 1 by pc. But r square cos square phi plus r square sin square phi will yield r square, implies r square will be equal to this much, implies r is equal to square root of r square plus mp minus 1 by pc whole square. So, now the value of Zm can be written as Zm equal to r plus I mp minus 1 by pc, which is equal to r cos phi plus I r sin phi, which is equal to r into cos phi plus I sin phi, which is equal to r into e to the power I phi. So, implies Zm is equal to r e to the power I phi, equation 15. Now, putting the value of Zm, in the expression for dy by dt, we can write, putting the value of Zm from this expression in the expression for dy by dt, we can write dy by dt is equal to f0 e to the power ipt divided by Zm. Now, this Zm can be omitted by this, and we can write this as r e to the power I phi, and taking this into up, we can write this as f0 by r into e to the power I pt minus phi 16. But our aim is to find the value of y. So, to get y, what we have to write? dy is equal to f0 by r e to the power I pt minus phi into dt. Now, integrating, taking the real part of e to the power I pt minus phi, because but e to the power I pt minus phi is equal to cos pt minus phi plus I sin pt minus phi, equation 18. If we take the real part of e to the power I pt minus phi, then it will be how much? Cos pt minus phi. So, this equation implies real e to the power I pt minus phi is equal to cos pt minus phi. Now, putting the real part of this e to the power I pt minus phi in the equation for dy, we can write dy is equal to f0 by r into cos pt minus phi into dt. This represents equation 20. Now, we arrived at equation for dy, but our aim is to find out the solution of the differential equation for forced oscillation, for which we have to find out the value of y. Here we have arrived at dy. So, it is very simple now to get y just by integrating this equation. Okay? Let us integrate this equation, and integrating this equation we can write y is equal to integration dy, which is equal to integration f0 by r into cos pt minus phi dt, and the integration of this f by r will be constant taken outside, and the integration of cos pt minus phi will be sin pt minus phi by p. So, it will be written as f0 by r into integration of this is sin pt minus phi divided by p. It can be further written as f0 by rp into sin pt minus phi. And to solve this, let us add pi by 2 here and subtract pi by 2 from here, and writing this we can get plus pi by 2 minus pi by 2, and it can be further written as f0 by rp sin pi by 2 plus pt minus pi by 2 plus phi, and it is in the form of sin pi by 2 plus theta, and which is known as your cos theta. So, we can write this equation further as f0 by rp into cos pt minus implies y is equal to this much. This is equation 21. Here this equation can be further written as, this equation 21 can be further written as y is equal to a cos pt minus pi by 2 plus phi, equation 22, where a is equal to F0 by Rp is equal to amplitude of forced oscillation. But we have already find out the value of R, but we have already found out R is equal to how much? R square plus whole square of MP minus 1 by PC whole root over. So this equation for A will become as A is equal to F0 by Rp, which is equal to F0 by P into root over of R square plus MP minus 1 by PC whole square. Equation 23. From the beginning, where we have taken the first differential equation for forced oscillation, we have taken R is equal to 2m, R is equal to 2 km and 1 by C is equal to S is equal to omega square m. The amplitude for forced oscillation now becomes as, in place of small r we will write it 2 km and in place of C we can write omega square m. So the expression for the amplitude of forced oscillation now becomes as A is equal to F0 by P into root over of 2 km square plus EMP minus 1 by omega square m by P whole square. Yes, on solving, this can be written as here m, here also m, all are in square term, they can be taken outside, and to here we can write this as F0 by m p within root over it is 4 k square plus P minus omega square by P whole square, and this can be rewritten as F0 by MP within square bracket it will be 4 k square plus it will be as P square minus omega square by P whole square. Now rewriting this as A is equal to F0 by MP, and here is one P, and if taken outside it will be P square, and if it is taken LCM then it will be 4 k square P square plus P square minus omega square whole divided by P square, and P square taken outside it will be MP to root over of 4 k square P square plus P square minus omega square whole square divided by P square. And if P square is taken outside then it will be P and P get cancelled, implies A is equal to f0 by m root over of 4k square p square plus p square minus omega square whole square. Okay. This is the expression for the amplitude of forced oscillation. Now, the solution of forced oscillation becomes as, now the solution of the differential equation for forced oscillation becomes as y is equal to a e to the power I pt, and in place of a we can write this term. So, the solution becomes as y is equal to f0 by m into root over of 4k square p square plus p square minus omega square whole square into e to the power I p t. f0 by m 4k square p square plus p square whole square. This is the solution for the equation of forced oscillation. This is the expression for the solution of the equation of forced oscillation. And from this expression, we have found that the expression for amplitude involves this factor, and the amplitude will be maximum only when the denominator will be minimum. And when maximum amplitude occurs, then the phenomenon is known as resonance. Now, our task is to find out the amplitude of resonance, that is amplitude resonance. Now, our duty is to find out amplitude resonance in forced oscillation. Before going to the details of amplitude resonance, let us first know what is resonance. Resonance is the phenomenon of setting a body into oscillations or vibrations when an periodic external force is applied on it, under the condition that the frequency of the applied force should coincide with the frequency of the vibrating body. Now, let us see under what condition this resonance occurs. And resonance is the phenomenon when the amplitude of the body is very large. Ideally, theoretically, the maximum value of amplitude at resonance is infinity. But this situation never happens because infinity cannot be reached. But practically at a resonance the amplitude is very high. Let us first calculate what should be the expression for the amplitude at resonance. That means we have to find out the maximum amplitude, because at resonance the amplitude becomes maximum, and we know the quantity which is maximum is nothing but a constant, and to get maximum amplitude we have to take the amplitude to be constant. If it is a constant, then its derivative will be 0. So, to find maximum amplitude, let us take the derivative of the amplitude with respect to the angular frequency of the applied force P. Now, to get maximum amplitude, let us take the derivative of this amplitude. That means, if amplitude is equal to A max d of A by dP will be equal to 0. So, d by dP of that value, which is if the amplitude A is equal to maximum, then its denominator will be minimum. If the denominator becomes minimum, then amplitude will become maximum, and the denominator will become minimum if its derivative becomes 0. The denominator will become minimum if its derivative becomes 0. That is d by dP of 4 k square p square plus p square minus omega square whole square will be 0. Now, rewriting this, we get 4k square into 2p plus 2 into p square minus omega square into 2p is equal to 0, implies 8 k square p plus 4p into p square minus omega square is equal to 0. If 4p is taken as common, 4p, then it will be 2k square plus p square minus omega square will be equal to 0, implies 2k square plus p square minus omega square will be equal to 0, implies p square is equal to omega square minus 2k square, implies p square plus 2k square is equal to omega square. Putting this value of p square from here in the expression for the amplitude, we can write A maximum amplitude at resonance will be equal to f0 by m divided by 4k square into p square. The value of p square is root over of 4k square into p square, which is omega square minus 2k square. plus p square minus plus p square, and in place of p square we can write omega square minus 2k square minus omega square whole square, and this can be written as implies A max is equal to f0 by m whole divided by root over of. Our duty was to find out the expression for maximum amplitude, which is known as the amplitude resonance. Here we have found out that A max is equal to f0 by m whole divided by root over of 4k square whole into omega square minus k square, and solving this we have found the expression for amplitude resonance as A max is equal to f0 by m whole divided by 2k into root over of omega square minus k square. This is the expression for the amplitude maximum or amplitude resonance in forced vibration. For ideal case, if there is no resistive medium, then there will be no frictional force, and in that case, if there is no frictional force, then k is equal to 0. So, putting the value k equal to 0 in the expression for A max, we can write A max is equal to f0 by m whole divided by 2 into 0 into root over of omega square minus 0 square, and something by 0 is nothing but your infinity. So, this A max becomes as infinity. That is, in ideal case, when there is no frictional force present, the amplitude resonance at resonance becomes infinity, and infinity is not practically achievable. Hence, the ideal amplitude of vibration at resonance is infinity, but practically this amplitude is very high. Now, we have taken p square as this much, omega square minus 2k square, and solving this we get p is equal to root over of omega square minus 2k square. But what is p? This is the angular frequency of applied force. Now, this can be written as 2 pi nu, where nu is the frequency of this applied force, and it can be written as root over of omega square minus 2k square. Further solving this, we get nu is equal to 1 by 2 pi root over of omega square minus 2k square. So, the time period becomes t is equal to 1 by nu, which is equal to 2 pi by root over of omega square minus 2k square. Here we have arrived at the expressions like amplitude at resonance, which is ideally infinity, but practically it is very high, and the expression for the frequency of the applied periodic force, and also this is the expression for the time period of the applied periodic force. So, friends, here today we have discussed the forced vibration, its equation, its solution, and the amplitude of vibration in forced oscillation, and the amplitude maximum which is obtained at resonance, and it is found that the amplitude maximum at resonance is ideal infinity, which is not practically possible, but the practical amplitude of oscillation in forced oscillation is very high. And here also we have calculated the frequency of applied force and also the time period of that periodic applied force which causes a damped oscillation into undamped, and hence due to the application of this applied force, the damped oscillation which becomes undamped is also known as forced oscillation. I hope friends you must have a clear understanding regarding your forced vibrations and amplitude of resonance. Okay, we will discuss sharpness of resonance in our next class. Many thanks.